You've probably heard someone say, new houses are being built too tight, and houses need to breathe. Well, this is half right. Houses do need to breathe. Deliberate and controlled fresh air delivered throughout a home is essential to maintaining a healthy indoor environment. However, leaky houses are a thing of the past. These days, houses are sealed against unwanted air entry and escape in order to achieve optimum air quality, comfort, and energy efficiency. Instead of random, uncontrolled air leakage, the proper way for a healthy house to breathe is through a well-designed fresh air ventilation system controlled by the occupants. Fresh outside air comes from a safe, clean location in just the right amount for the size of the house and the number of people living there. Research has shown that air entering older, leaky homes can come from potentially unsafe sources, such as basements, crawl spaces, or attached garages. The random cracks, holes, plumbing, and electrical openings that let air in from these spaces also provide pathways for unwanted pollutants and pests. In this video, we'll show you the different types of residential fresh air ventilation systems and explain how to identify and implement the best system for your needs. It's divided into segments so you can easily get to the information that's important to you. However, before we get into the details of mechanical systems, let's take a quick look at why ventilation is needed in the first place. Ventilation is becoming increasingly important as new and properly weatherized houses become tighter and less drafty. Centuries ago, Benjamin Franklin famously stated that, "I am certain that no air is so unwholesome as air in a closed room that has been often breathed, and not changed." Not only was Ben Franklin correct about stale, unwholesome air, but did you know that in a poorly ventilated home, the amount of moisture that builds up just from breathing and everyday activities can be enough to create condensation and mold growth? Mold in your home can lead to serious health issues and expensive property damage. You can find more information about mold causes and prevention in the video at this link. In addition, common household items can emit harmful pollutants into the living space. Examples include cleaning and personal care products, paints, wood-burning stoves, and gas appliances, as well as outgassing from things like floor coverings, finishes, and furniture. Health effects associated with poor ventilation and unhealthy indoor air quality can lead to missed school and work, increased doctor visits, medication use, and even hospitalization. So it's fair to ask, what's wrong with natural ventilation? My house has windows, so why not just open them all up and let the air in? For most places in the U.S., this is not an ideal option. In addition to the inconvenience, comfort and energy efficiency problems result when outside air is too hot or too cold. Furthermore, open windows allow pollen, dust, and other contaminants into the home, and security and noise can be an issue in some neighborhoods. Ideally, houses should have two types of ventilation systems: spot ventilation and whole house ventilation. Spot ventilation, familiar to most folks, consists of a basic exhaust fan located in a place where moisture and pollutants are produced, such as a bathroom, kitchen, or utility room. The other ventilation system, the focus of this video, is the whole house fresh air ventilation system. Whole house systems are the best way to safely guarantee a reliable daily fresh air exchange throughout the entire house. There are three main types of whole house systems: exhaust-only systems, with or without fresh air inlet vents; integrated systems, where outside air is integrated or mixed directly into the home's forced air heating and cooling system; and heat and energy recovery systems known as HRV or ERV units. In the segments that follow, we'll cover the details of each system and provide information on their operation, installation, inspection, and implementation. You can watch the entire program or simply choose the segment or segments that relate to your situation.
When it comes to whole house ventilation, the exhaust-only fresh air system is the lowest cost and simplest technology. In this type of system, one or more exhaust fans is installed in a central location where it removes pollutants and moisture, much like a bathroom fan or kitchen fan, and pulls fresh air into the home from outside. Air out equals air in. But unlike a typical bathroom fan, these whole house fan units are much quieter and can exchange more air and include automatic controls built into the unit or as a separate controller. These automatic controls provide continuous or near continuous operation, so the occupants don't have to remember to turn the system on and off. They are relatively inexpensive to purchase and install, and they are designed to use very little electricity, about the same as a compact fluorescent light bulb. The exhaust action of a whole house fan creates a slight vacuum inside the home. This causes outside air to be drawn in to replace the air being pulled out of the living space. In an exhaust-only system, the air enters in one of two ways: through intentional air inlets known as trickle vents, or through random house openings, air leaks. Fresh air exchange at the correct rate has minimal effect on comfort and does not significantly increase energy costs, because all houses leak air anyway. But as mentioned in the introduction, random air leaks may bring in air from crawl spaces, cellars, garages, building cavities, or other locations that can be sources of unwanted moisture, odors, or pollutants. To help avoid this, houses can be fitted with trickle vents, dedicated fresh air inlets, built directly into window frames or installed through exterior walls. These simple vents are intended to provide controlled fresh air entry from appropriate locations. The vent should have insect screens and be located so they don't bring in contaminants from the outdoors, away from driveways, clothes dryers, and kitchen exhausts, for example. The screens should be routinely checked and cleaned to maintain consistent airflow. Consistent fresh air exchange allows houses to breathe properly, reducing exposures to indoor air pollutants and protecting against mold and moisture problems. In an exhaust-only ventilation system, however, air is reliably exchanged only when the central fan is on, so it is recommended that it run continuously, day in and day out. The system should be run with a timer control for automatic operation. Just set it, forget it, and enjoy a home with fresh air. The cost of operating these new, quiet, energy-efficient fans is relatively low, around 33 cents per day or $120 a year, based on average electric rates. This includes both the cost to power the fan and the cost to heat the incoming cooler air. If occupants choose not to leave the system on full time, the controller should be set for a minimum of 8 hours of fresh air each day. But note that according to the latest standards, if the fan is set to run less than 24 hours, higher exhaust flow rates must be used. Higher exhaust flows mean a noisier fan and possible comfort issues. It is best to choose a quiet, energy-efficient fan sized for continuous operation. The exact amount of ventilation needed for a particular home is determined by the house size and the number of bedrooms or occupants. This is covered in more detail in Segment 5, Installation and Inspection. An essential consideration for this type of system is to make sure that air from each room in the house has an easy pathway to the central exhaust fan. Without these pathways, pollutants and excess moisture can potentially build up in certain areas, and incoming fresh air may not circulate to all rooms in the living space. A common method of providing air pathways is undercutting the doors of bedrooms and other rooms. This creates a gap for air to flow in and out. Door undercuts should be about 1 inch above the floor or carpet for each register in the room. However, in some cases, this could result in an unsightly gap. 2 registers in the same bedroom, for instance, would require a 2-inch door gap. Another option is to install grills in the walls. These allow air to flow even when the doors are tightly closed. If light or noise is an issue, one grill can be located low on the wall and the other high on the opposite side of the wall between the same studs, using the uninsulated interior wall cavity as the pathway. Another alternative is a short duct known as a jumper duct. Typically installed in the ceiling, these ducts connect rooms to the central core of the home, providing an easy pathway to the whole house fan. When properly set up and operated, the exhaust-only whole house ventilation system can be an effective and affordable choice for proper ventilation. The key elements are proper fan sizing, consistent operation, and consideration of the fresh air pathways into the entire home. You want to make sure clean, fresh air can reach all areas and people inside, and any pollutants and excess moisture can be effectively removed. In this segment, we're going to talk about the type of whole house ventilation system that is integrated into a home's central heating and cooling system. Instead of a standalone exhaust fan unit, the existing forced air system is used to pull in, mix, and deliver fresh air throughout the house. Outside air enters through an intake grill on the home's exterior. It is important to locate this intake away from potential pollutant sources, such as driveways, clothes dryer vents, or exhaust from gas heaters or other combustion appliances. The grill must also be screened to keep out insects and other pests. The outside air comes in here and feeds into the return or suction side of the furnace. When the furnace fan turns on, it pulls fresh air into the system and circulates it to the rest of the house through the existing air ducts and registers. It's important that just the right amount of fresh air is delivered through the intake duct. Too much outside air creates comfort problems and heating and cooling costs go up. Not enough outside air can lead to buildup of indoor pollutants, excess moisture, and associated health issues. To ensure adequate ventilation, the intake duct has a flow regulator that must be manually set to meet the prescribed rate of airflow when the system is installed. The proper amount of flow, measured in cubic feet per minute or CFM, is based on the size of the house and the number of bedrooms or occupants. Determining the correct flow rate for a particular home is covered in Segment 5, Inspection and Installation. Okay, now that the amount of outside air is properly set, a mechanism is needed to control when the fresh air is allowed into the forced air distribution system. A motorized damper with manual and automatic controls opens and closes to bring in fresh air to meet the needs of the occupants. Unless there's a shutoff damper, fresh air will be pulled into the system whenever the central fan is running. However, on certain occasions, people may not want or need a continuous supply of outside air, for example during extreme hot or cold weather. On the other hand, fresh air ventilation is often needed at times when the heating or cooling system is not running. This is why an integrated whole house system must also include manual and automatic timer controls to operate the fan and open the damper for fresh air. This can be a simple clock timer with movable pins, a digital clock timer, or time controls built into a sophisticated thermostat. The controller can be set to turn on the furnace fan, but without the furnace providing heat or the air conditioner providing cooling. Or the occupants can temporarily set the heating or cooling system to operate normally, but block outside air from entering when it is too hot or too cold outside. An advantage of an integrated system is that by using a home's existing air distribution system, adding the components is relatively easy, and the correct amount of fresh air is delivered throughout the home. A downside of this system is the increased cost of running the large central fan for ventilation. The fan for a central forced air system is larger and uses much more electricity than the small, quiet, and efficient fans used in other ventilation systems. Based on typical U.S. electric rates, using the fan 9 hours per day would cost about $140 a year. However, it is generally recommended to run whole house ventilation systems for 24 hours a day, increasing the annual cost to about $375. Energy codes in some states require more efficient fan motors called ECMs. An ECM is a variable speed motor that will use less electricity at lower speeds than a standard motor. However, even with these motors, an integrated whole house ventilation system is still the most expensive system to operate. Now let's take a look at the whole house fresh air ventilation systems known as heat recovery ventilation and energy recovery ventilation, commonly called HRV and ERV. These balanced systems have some advantages over other systems. Despite a higher initial cost, they can be the most effective, efficient, and inexpensive to operate on a daily basis, especially compared to the integrated system. HRV and ERV systems use two small, quiet fans, one to draw fresh air in from the outside and the other to remove and exhaust the stale indoor air. The two air streams pass separately through the unit's exchange core, where heat is recovered from one airstream and transferred to the other. In winter months, the incoming cold, fresh air passes through the exchange core, where it is warmed by the outgoing stale air from the warm house. On the flip side, during hot weather, incoming fresh air is cooled by the exhaust air if the house air is cooler than outside air. HRVs and ERVs are not heating or cooling systems in themselves, but by tempering the incoming fresh air and recapturing a portion of the energy used to heat and cool a house, they can increase efficiency and reduce overall energy costs. Since the fresh air is tempered, comfort can be improved as well. The HRV, heat recovery ventilator, is designed so the incoming and outgoing air streams do not mix. The exchange core transfers only heat from one airstream to the other. Airborne pollutants being flushed from the house cannot cross-contaminate the incoming fresh air. In addition to transferring heat, the ERV, energy recovery ventilator, also captures moisture and transfers it from the more humid to the less humid airstream. It should be noted that with ERVs, there is the possibility the shared moisture could contain some pollutants. Both ERV and HRV units include air filters to keep debris and particles from clogging the core. The filters also clean the fresh air delivered to the home, helping reduce exposures and keeping the home more dust-free. They should be checked regularly to keep the system running at peak efficiency. In a typical HRV or ERV setup, the tempered fresh air from the exchange core is delivered directly to living areas and bedrooms through dedicated supply ducts. The outgoing stale air, containing moisture, odors, and particles, is collected from the bathrooms, kitchen, and sometimes a utility or laundry room. The return air is ducted to the exchange core, where it tempers the incoming fresh air before being exhausted out of the house. These systems are normally operated through a central control panel that can be programmed in a variety of configurations. Options like intermittent run times, high, medium, and low speeds, exhaust only, recirculation mode, and so on. In spite of these options, simple control strategies usually work best. Occupants can select a single fan speed setting that will achieve the recommended flow rate and leave the system on all the time. To determine the flow rate that is best for a particular system and home, refer to the information found in segment 5 of this video, Installation and Inspection. Most systems can be installed with exhaust boost timer controls located in bathrooms or other areas where stronger, temporary exhaust airflow might be desired. The unit's two fans temporarily go to a high-speed setting for a specified amount of time. From a performance standpoint, HRV and ERV systems are arguably the most effective and efficient of all whole-house ventilation systems. As mentioned, they tend to be considerably more expensive to install, but some of the extra costs are offset by energy savings. They also take up more space, and the installation, maintenance, and controls can be more complicated. However, the higher cost when spread out over a 30-year mortgage is one of the best investments one can make in terms of money and health.
Installing and inspecting a mechanical ventilation system is not rocket science. However, a few things need to be done to make sure you'll have a fresh air system that works as planned, is economical for the homeowner, and provides a healthy environment for the occupants. Before planning and installing any type of ventilation system, you'll need to determine exactly how much fresh air the system needs to deliver. Ventilation airflow standards are measured in CFM, cubic feet of air per minute. A table of the latest residential requirements lists CFM ratings based on the size of the house and number of bedrooms or occupants. If we take the example of a 2,000 square foot home with 3 bedrooms, it's easy to see that the requirement specifies a ventilation system capable of 60 CFM. At this rate, assuming 8-foot high ceilings, about 1/3 of the air in the home is exchanged every hour. Now let's talk about the 3 types of whole house systems discussed in segments 2, 3, and 4. For an exhaust-only system, if possible, choose a central location for the whole house fan. If it's a 2-story house located on the upper floor, the code doesn't specify where the fan should be installed, but a central location will improve the system performance. Follow the manufacturer's installation instructions and install all associated parts. When it comes to installing the ductwork, short, straight, and smooth is best. Exhaust fan ducts need to be sized according to the length of the run and the number of turns, bends, or transitions installed. The longer the duct and the more turns or transitions, the less air the fan will be able to exhaust. In addition, flexible ducts, which have ridges, create more air resistance than smooth-sided ducts. This chart specifies the size, length, type, and number of bends or transitions for each duct based on the size of the exhaust fan unit being installed. Note that the minimum diameter is 4 inches, but smooth wall ducts allow a much longer duct run. Both types of ducts allow up to 3 elbows or 90-degree turns. Again, the fan will operate most efficiently with the shortest, straightest, and smoothest duct installation. Ducts outside the heated space, such as through an attic or crawl space, must have R4 insulation to keep moisture from condensing on the inside. The exhaust duct must be vented all the way outside the structure and connected to an appropriate roof cap designed for this use. Here are some other things to remember for exhaust-only systems. When connecting the duct to the fan, do not use screws that may interfere with the damper opening. Fan controls must be clearly labeled and operating instructions left at the house. If not, the occupants will probably not know how to properly operate the system. Now let's talk about the type of ventilation system that's integrated with the furnace. To make sure it's installed correctly, the incoming fresh air duct should be attached to the return plenum within 4 feet of the air handler. Never attach the duct directly to the furnace cabinet. There should be 2 dampers in the fresh air duct. One is a fixed flow regulator that must be calibrated to deliver the proper amount of fresh air to the system. Place an accurate flow hood over the exterior intake grill and adjust the damper to the CFM rate specified in the ventilation requirements. Make sure the furnace fan speed is set to the proper setting during the adjustment. The second damper is motorized and can open and close as the system calls for ventilation. This damper is controlled by the occupant, either manually or by automatic timer control. The latest code also requires that the furnace have an ECM motor. An electronically commutated motor is a variable speed motor that will run at a lower speed during ventilation mode and saves the owner on their energy bill. The ECM motor should be set at the lowest speed for ventilation. Heat recovery ventilation and energy recovery ventilation, HRVs and ERVs, are balanced systems. This means the amount of fresh air flowing into the home must be the same as the amount of stale air being exhausted. To accomplish this, it's necessary to measure the incoming and outgoing air streams in each room and use balancing dampers to equalize the rate of flow. The main unit should be installed in an area accessible to the homeowner since it requires regular maintenance such as filter cleaning or replacement. Size, length, and transition requirements for ductwork will depend on each unit's specifications. In order to meet code, all the components of an HRV or ERV system must be installed according to its manufacturer's specifications. Now let's talk about ventilation strategies to improve air quality in existing homes. Often these homes rely on natural, uncontrolled air leakage through the building's shell for air exchange, or occupants will simply open windows and doors when they notice excessive moisture or stale air. As we showed in segment 1, opening windows and doors is not the most effective, comfortable, or efficient remedy. And uncontrolled air infiltration through the holes, cracks, and crevices of your home provides little assurance that indoor pollutants and excess moisture will be flushed out and replaced with clean outside air. Studies have shown that as much as 40% of the air coming into our homes through leaks comes from the below-house crawl space, and an additional 17% or more can come from an attached garage. These are areas not commonly associated with healthy air. A good first step toward improving air quality in an existing home is to find and seal air leaks. It's unrealistic to expect to seal all the leaks, but a significant reduction is usually possible. In addition to helping improve indoor air quality, air sealing increases comfort and lowers energy bills. For a more in-depth look at air sealing, follow this link. The next step is to measure the air tightness of the house and estimate the amount of natural air leakage. This is done with a blower door test conducted by a trained technician. The leakage rate calculated from the test results is compared to an accepted residential standard for ventilation. If the estimated natural air leakage rate is less than the accepted standard, fan-powered mechanical ventilation must be installed to help provide occupants with adequate fresh air. Depending on the amount of air exchange needed, a whole house fresh air system or individual source exhaust fans can be used. Most mechanical ventilation standards are based on the American Society of Heating, Refrigeration, and Air Conditioning Engineers, ASHRAE, Standard 62.2. More details concerning the standard's application to existing construction, as well as related formulas and calculators, can be found in these links. The leakage rate, when compared to the accepted standard, will determine the flow rate and daily runtime needed for a ventilation system for the home. The estimated natural air leakage of a home can be used to offset some of the mechanical ventilation needs. For example, if a house is estimated to already leak half the ventilation required by the code, then the capacity of the new ventilation system could be downsized by 50%. In some houses, existing spot or source ventilation, such as kitchen or bathroom exhaust fans, may be able to meet the whole house requirement if these move enough air and are operated continuously or are reliably cycled on and off by automatic controls. However, existing local exhaust fans are likely to be loud, which can discourage proper runtime. They also don't circulate fresh air throughout the house, as well as a dedicated whole house system. To provide improved fresh air distribution, installing one of the 3 types of whole house ventilation systems might be a better choice. These are covered in segments 2, 3, and 4. If existing exhaust fans don't meet the local spot or source ventilation requirement, you can increase the whole house ventilation requirement to compensate for the insufficient fans. However, it's recommended that the fan flow rates meet requirements in areas that emit significant water vapor and pollutants, such as bathrooms with showers and kitchens. For a fan that operates when needed, many standards require an exhaust fan system be no louder than 3 sones. A sone is a measure of loudness. However, if this fan is also to be used for whole house ventilation, it can be no louder than 1 sone. Existing fans that are being left in place are exempt from these sound requirements. Whether they already exist in the home or are newly installed, it's recommended that all fans be tested to ensure they're operating at the intended or designed flow. Testing may also be a requirement if participating in a local weatherization program. We hope you've benefited from watching this video. Remember that fresh air ventilation is important for the health of both the house and the occupants. Stay tuned for a list of additional resources. On behalf of our sponsors and my colleague Rich Prill, I'm Dave Blake.